Welcome to Ask and Learn.
We're asked to prove that S is zero related to T if and only if S and T are both final states or neither are final states. So first, let S be zero related to T. This is part A, by the way. This implies that f of Sx and f of Tx are both final or non-final states for all strings x such that the length of x is less than or equal to 0. In other words, since lambda, the empty string, is the only string of length 0, it follows that f of s lambda and f of t lambda are either both final or both non-final states, where lambda is the empty string. Now we have that by definition, f of s lambda is s and f of t lambda is t. So we have that S and T are both final states or both non-final states. Now, that was one direction. We want to prove the other direction. So let's suppose that S and T are both final states or neither are final states. This implies that f of s lambda and f of t lambda are both final or are both non-final states. Since lambda is the empty string, and this is true by definition. Now, lambda is the only string of length 0. So it follows that f of s x and f of t x are both final or non-final states for all strings x of length less than or equal to 0. Therefore, it follows that s is 0 related to t. And this is what we wanted to prove. So we've shown s is 0 related to t if and only if t and s are both final states or neither are final states. Now we're asked to conclude that each final state of 1 over m, which is an R star equivalence class, contains only final states of m. So let A be an equivalence class of m. M bar. Now this implies that A is an R star equivalence class of M. So all states in A are either all final states or are all non-final states in M by a previous exercise. And this implies that all final states of M bar are also final states in M. Now in part B, we're asked to prove that if k is a positive integer, then it follows that s is k related to t if and only if s is k minus 1 related to t and f of sa are k minus 1 f of ta for every a in the language. So let k be a positive integer. Now suppose that s is k related to t. Then it follows that f of sx and f of tx are both final states or are both not final states. For all strings x of length less than or equal to k, now let y be an input string of length k minus 1. And let a be an element of the input set. So since y is an input string of length at most k, it follows that s is k minus 1 related to t. Now ya is the strength of length at most k. Well, we have that f of s a y is equal to f of s a y and f of t a y is equal to f of t a y. So it follows that since the length of ay is less than equal to k. In fact, it's going to be equal to k. It follows that f of SA is k minus 1 related to f of TA. So that proves one direction. Now let's suppose instead S is k minus 1 related to T. And that f of SA is k minus 1 related to f of TA. For all inputs A. Then it follows that f of Sx and f of Tx are both final states, or are both not final states. For all strings x, such that the length of x is less than or equal to k minus 1, we also have that f of s xa and f of t xa are both final or are both not final for every input string x with the length of x being less than or equal to k minus 1. This is because f of s xa is equal to f of s x a, or sorry, f of s a x and f of t x a is equal to f of t a x, and we know that those are k minus 1 related. Now let y be a string of length at most k. Now suppose that y is a length of at most k minus 1. Then clearly we have that f of s y and f of t y are both final or non-final states. Now suppose instead that y has a length k. Well, that means we can find a z such that y is equal to za, with the length of z being less than or equal to k minus 1, a being a single input, and so it follows that since f of s y is equal to f of s za, which is equal to f of s a x, and we have the f of t y is equal to f of t za, which is equal to f of t a z. We know that f of s a is k minus 1 related to f of t a, and therefore it follows that f of s y and f of t y are both final, or are both non-final. So it follows that s is k related to t if and only if s is k minus 1 related to t, and f of sa is k minus 1 related to f of ta for all inputs a. Therefore, we're asked to conclude that the transition function f bar is well defined. Well, we've seen by proving this previous statement that f bar does not depend on the choice of the representative from the equivalence class. Therefore, it follows f bar is well defined. Finally, in part C, we are asked to describe a procedure that can be used to construct the quotient automaton of a finite automaton M. So let M be a finite automaton. Now, what we want to do is test every pair of states for k equivalence in M. for each integer k from 0 up to n, where n is the number of states in M, now this implies that we need to make sure that the finite state automaton ends up in the same state for every input string of length k. And there are only a finite number of strings of length k. So this is possible. Now, n, the number of states in M, is the smallest integer such that the n equivalence classes are the same as the n-1 equivalence classes of M. We proved this in a previous exercise. Therefore, we can stop determining equivalence classes once we obtain the same equivalence classes as for the previous value of k. And it follows that these n equivalence classes of M are thus the states of M star.